Hello, everyone. Welcome. Thanks for joining our diagnostic training session today. And what you're about to see is a pre-recorded training session we did over in the United States. But be assured that a lot of the material that we cover is really applicable to any automotive application. So just be aware that yes, it is a lot of North American vehicles, but they will apply a lot of the same principles apply over in the UK as well. Now, if you do have any questions, if you're watching this during the premiere, you can just leave it in the chat. We'll be monitoring live chat. If you're watching this after the premiere, then just feel free to leave a comment underneath the video and we'll get to those as we can as well. So my name is Jason Gabrenas. I'm one of Snap-on's diagnostic technical trainers. I've been in the training department since 2013, traveling around North America, helping techs and shop owners get the most out of their diagnostic equipment. Before I did that, it was a couple years as a diagnostic sales rep at Snap-on, so I had 30 different franchisees I worked with, as well as the shops that they serviced, in order to help everyone get the most out of their diagnostic needs. Then before I did that, it was 8 years at Subaru. So I worked in a dealership, and over time, I guess, just became the default diag guy in the shop. So I always ended up having the drivability problems, the intermittent problems, the weird wiring problems that would show up on those cars. And that's really where I cut my diagnostic teeth, was trying to figure out all those weird head scratcher type cars that would come into my bed. Then before that, a bunch of other miscellaneous wrenching jobs. Been a little over 25 years under hood experience for me. Our topic today is component testing and correlation. Now, I know we talked quite a bit about testing individual components. We did a whole series over the summer, but sometimes it's always good to go back to remembering, why are we even do this in the first place, and how can we use a same time base on the scope in order to find correlations between different signals on the same sensor, or maybe it could be different sensors that are related. We'll talk about a couple different ways that we're going to go through that. We have to remember, think back to how does a vehicle's computer work at the most basic level, right? And really any computer, any module on a vehicle, think of it like a house. It's got a front door and it's got a back door. Coming in that front door is going to be all of my inputs. So my NOx sensor, my oxygen sensor, my coolant temp sensor, all those inputs come into the computer. Then the computer processes them however it's programmed to do that. And then it spits that data out the back door and presents it to the scan tool. So if I'm only looking at data on a scan tool, yes, it is useful. Yes, it is a piece of the puzzle, but I'm only looking at half of what's going on. I'm only looking at the signals after the computer's already interpreted them. And it's not always 100% accurate as to what's going on with the car. It's really showing you the effect after it already happened. Good friend of mine says, computers don't lie, they get lied to, right? So if my inputs are wrong, then my outputs will be wrong as well. But why is that? There could be many reasons why they might be. So we always want to try our best to test at the source, at the component, or somewhere between the component and the PCM before the computer gets its grubby hands on the signal and has a chance to change it, right? So we want to always make sure we're testing the component directly. And I think in this day and age, with the supply chain problems that we've been having and things like that, we want to make sure that we're testing it right the first time and being sure. So why did we start using scopes? Well, it's for really that reason, is we need to be able to test the different components on a vehicle. And back in the day, not even that long ago, really, but digital multimeters, they really don't react fast enough for these computer controlled circuits and these faster reacting sensors on these vehicles nowadays. It does have its uses in some cases, depending on what we're trying to do, but really a meter doesn't react fast enough. We really need to use something with a high sample rate, like a lab scope or guided component tester, as it were. So we think about newer cars, and even newer than what we're talking about here, 06, 96 and newer, the speed that the systems are checked, they call that the sample rate. So on a car's computer, on the input side, it's going to sample those signals a certain number of times per second, however fast the processor is able to do so. So then it takes that sample and it makes its calculations, and then it sends out the data. So it's a lot faster than it ever used to be before. So if we think all the way back to the 80s and 90s, when computers first started showing up on cars, up until maybe OBD2, a 500 millisecond glitch on a car wouldn't have affected the car in any way, shape, or form. I can be driving down the road and then I lose a temperature sensor input for half a second. Car doesn't even realize anything happened because the sample rate of the module was not as high as it would be today. So it wasn't even looking at it at the time when it glitched. It could happen. So today, though, a 500 microsecond glitch can really bother a car. 500 microseconds is 500 millionths of a second. So take a second, divide it into a million little pieces, take just 500 of those. That's not a lot of time. That's crazy small amount of time. So we need to be able to catch those. Now, even the best digital multimeters out there, talking about sample rate, they only sample and display 250 every 250 milliseconds. So that is not fast enough to catch a 500 microsecond glitch if it happens when it's not looking at it 4 times a second. Right, 250 milliseconds is 4 times a second. So we need to be able to look at it with something with a higher sample rate than what we might be used to using. That's why we need to do these direct component testing. Let me just give you an example of what we're talking about here. You may have seen this before, but top left-hand corner is scanner data, process data coming out the back door of that computer, as we said before, on an oxygen sensor reading voltage. This part of the window down here is a scope hooked up to the same oxygen sensor reading the same voltage. These 2 red boxes show the same amount of time passing. And I think you'd agree there's a big difference between these 2 different patterns. A lot more detail in this pattern right here. These 2 little dropouts right there happened. And if you were only relying on the scanner data to look at this, you would have missed those. Now, is it a fault of the scan tool or is it a fault of the car? I'm going to go blame the car because of that sample rate we were talking about earlier. So the car has to look at the signal, process it, spit it out the back, send it to the scan tool to show it. Sample, calculate, send it to the scan tool. Every time it does that, it takes a little bit of time. Now, granted, on a newer car, it takes less time, but it still takes a little bit of time. And every time that handoff occurs, we are losing that little bit of resolution on the signal. So it doesn't matter what kind of scan tool you have. No matter how fast it samples, it's still limited by the computer in the car. Right? So being able to look at the raw data with the scope, that is where that really comes in play to help us out, especially on things like comebacks and intermittents. Now, I know in my world, that's 2 4-letter words for me, comebacks and intermittents, because we don't like any of those, right? We don't like working for free. And intermittent problems happen on the 3rd Thursday of the month under a blue moon, right? So we want to make sure we can maximize our time when it comes to diagnosing a vehicle. So it's all about verification. Verify, 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 and then verify again, right? Because the scan tool only shows us the effect. Remember, we talked about that. It's coming out the back door process data. It's a good clue. It's going to point us in the right direction, show us where we need to look, where we need to go, but it's still only the effect. We need to verify that problem and then verify that repair as well. So if we think about, let me give you a little for instance. Get a car comes in, it's got a P0102 code, mass airflow sensor. So you go through, check the flow chart if you have one, and you say, all right, well, according to this, I guess it needs a mass airflow sensor. So I'll call the parts store. Call the parts store, say, okay, I need a mass airflow sensor for XYZ car. They said, yeah, I got 3 in stock. I'll send it over. Or maybe they're like, oh yeah, it's a 2-week lead time on that. You never know. But anyways, part comes in, you put it in the car, you send the car on down the road, and you say, oh man, I really, really, really hope that car doesn't come back. Now, how about instead of crossing my fingers and hoping really hard that car doesn't come back, how about I test the part first? Test the part, verify that it has failed. If it has failed, I can be a lot more confident in ordering a new one. Then when the new one comes in, before that car leaves your site, test the new part. And you might be asking, why am I testing a brand new part? And I'll ask you, have you ever gotten a brand new part in a box that didn't work? Happens all the time. And then, like I said, supply chain issues being as they are, it could wait 2 weeks for a part sometimes nowadays too. So we don't want to have to worry about that either. We want to be as close to certain as possible. And that's why we want to be able to test. Don't guess. That's what we always used to say. Test, don't guess, right? So we want to be able to test and verify. And you might be saying, well, the flow chart will tell you. No, it won't. Not always. I think back to my days in Subaru. I remember one time I had a car, came in, it had a P0340 something. I think it was a cam sensor code, regardless. I don't remember the exact number, but it was a cam sensor code. And if you look through every line on that flow chart, not once does it ever say to test that sensor, look at the sensor, or replace the sensor. So you mean to tell me that I'm getting a code for a cam sensor and nothing is wrong with that sensor? And nothing could possibly be wrong with that sensor because I'm not actually testing the sensor. All right. So I learned real quick that don't trust the flow chart all the time. Test the part. Right. It's always best to go direct to the part and test it and verify. And where do I get that information? Well, if you have a Snap-on tool with a scope in it, you will have the guided component test database in there as well. So it gives you a wealth of information, and we'll look more about this as we go on. But it gives us operations, location, connector views, tech notes, and anywhere between 1 and 6 different tests that we can do on a component. All told, inside this database, there's over 5 million guided component tests, goes back to 1981. It is a wealth of useful information, definitely well worth it. By doing this, by having this information in my tool, it avoids unnecessary parts replacements because I'm actually going to test it. Of course, you have to use it to do it, but it avoids unnecessary parts replacements because I'm verifying that I don't have a problem with the part, or maybe I do have a problem with the part and I can verify that I do. All right. In turn, by doing so, that can help prevent comebacks. Now, it's not going to 100% eliminate every single comeback, but on the misdiagnosed parts, that can definitely reduce those comebacks. In turn, that helps prevent the loss of a customer. Just think about that. You think about a comeback. What's worse than a comeback? A never comeback. Now, what's a never comeback? Car went to your shop, you went through, you thought you got it right, and the car never came back. Little did you know that the customer had the same problem 3 days later and said, all right, forget this. I'm just going to go to a different shop and see if they can figure it out. And sure enough, they go to the different shop and they do figure it out. And at that point, you're out of customer, right? Because they're probably going to go back to the shop that fixed it right the first time, right? Flip side of that, though, if you become that shop where you're the go-to shop in town and you're testing and you verify everything, that can help attract new customers. You get that reputation in town. It's like, hey, this is the place to go because they fix it right. And they, I've never had a trouble there. And then all of this rolls into help the shop's profitability. Now, whether or not you are a shop owner or an employee in a shop, having a profitable shop to work at is a good thing for everybody, right? So just take all that into consideration, testing the part. Now, when we're testing a part, we have to take into consideration different modes of component failure. Now, if I'm going to think about how a component can fail and how I'm going to test it, it really falls into these 3 buckets. All right, these 3 buckets is how it pretty much how it's going to fall. We're going to have an open, a short, or resistance issue. So an open would be maybe I have no voltage to the component. Right, voltage supply, it's open, and I'm not getting any voltage. No voltage from the component. Many components will have power, ground, and then a signal returned back to the computer. Maybe that signal's not making it back to the computer, right? So that's an open that way. Or we could have a short. Think about excessive voltage. So if I have a short inside the harness, I have a 5 volt rubbing on a 12 volt wire, and they short together, then I could have extra voltage going through that 5 volt wire that I don't want. Or I could have insufficient voltage. If I have a short to ground, let's say it's rubbing on the engine block or something, and then it's just shunting that voltage to ground. Could be an internal short to ground as well. So instead of getting 5 volts, I'm getting half a volt, right? That could be a problem as well, and that would be a short. And then resistance, right? We've all seen that before. Well, maybe not everybody, but I know in my part of the world, we get a whole lot of corrosion out there because of the stuff they put on the roads mainly. But you pull that connector apart and you see all the green fuzzy stuff, right? That increases the resistance in the wire, in the connector, increases the amount of amperage and voltage needed, also would cause a voltage drop to be measured. And think about damage, right? Talked about that rubbing on the engine block. If I fray a wire, even if it's not shorting right now, that could cause a resistance issue even when it's not shorting. It could just be, think about a multi-strand wire. Right? Let's think about like maybe a battery cable, right? Lots of multi-strands. If I were to take my ohm meter and put it on the either end of that multi-stranded battery cable, I'm probably going to get 0 ohms or pretty darn close, right? I'm going to have continuity. Now, let's say I take one single tiny strand of that
multi-stranded wire out and do the same thing, put my ohm meter on either side. Probably still going to get 0 ohms, no excessive resistance continuity. But will that tiny little strand of copper wire start a car? Not going to be able to carry the amperage. It's going to get really hot if it tries, but that's a resistance issue. And you're really not going to be able to tell it with a ohm meter. Really, you need to load the circuit, ideally. So maybe like a headlight or something like that, a lot of folks use. But you might also be able to tell by doing a voltage drop in there too, and seeing where the voltage drops off in the circuit there. So these are the ways we can test. Now, why would I want to use multiple channels? If I can read the signal by using multiple channels on the same time base, that's the key right there. So I know there's other scopes out there that allow you to set up whatever time base you want on whatever channel. But in my mind, that defeats the purpose of what we're trying to do if I'm using multiple channels. I need to be able to see them reacting on the same time base. Otherwise, it's going to skew everything all over the place. And I'm not going to be able to tell, okay, so when this happens, what happens here, right? You need to have that consistent time base on there. I know I get that asked that question every once in a while, is why does Snap-on have a one time base for all the channels? That's why. So you can see how do they compare to each other on the same time base, because we have to have that constant in order to be able to do it. So in this case, it's a cam and crank correlation, and I can see my crank sensor there, and I can see my camshaft sensor there, and see how the signals fall and see whether or not I'm in time. So let's talk about a couple different components and a couple different ways that we can use multiple channels to test and learn more about it. So if we talk about a fuel injector, there's 3 different things that we can test just on a fuel injector itself. So we can check it electrically, check the voltage flowing through the circuit, verify the circuit integrity, verify the component operation itself. If certain things happen in the signature, we know that it opened and closed. Mechanically, I can view current flow. So I can see how is it working internally, how are the windings, verify that it even opens. We'll talk about that in a second. You can see where that pintle actually opens when using a current test. And then hydraulically as well, if you wanted to use a pressure transducer, you can look at the pressure change, pressure drop in relation to, if I compare 2 of these things, if I have a pressure transducer and an electrical or mechanical on another channel, I can verify the state of flow. If I see that injector commanded open, right? So I see my pattern and the injector's there, and my pressure doesn't move, then that injector really didn't open. Maybe mechanically it opened, but it didn't spray any fuel, right? We can see that. We can see how it drops off. And then maybe if it drops off excessively, then that could be another problem entirely. Or if we see that it doesn't build up the proper pressure, maybe it's not closing all the way, it's leaking, right? So we can see all these different things by being able to compare. So if you're here at the very beginning, we talked about this in the pre-roll video, but to reiterate, because I know not everybody was here, here is a standard gasoline fuel injector looking at the voltage and the current flow through that injector. So on a standard gasoline fuel injector, usually it's going to be powered by a relay, fuse relay type thing from the fuse box. So I have constant power, and if I back probe at the injector, we'll see constant power. If so right here we see about alternator volts, about 13. So it comes in and it pulls it down to ground. Now, when it turns on, that is where we see it pulling down to ground, because that is the injector driver grounding the circuit. It's causing voltage to flow through. So I should see about ground here, which I do. It's around about 0. Then from here to here, both sides of this box on this injector, that is the injector on time, commanded on time. You want to make sure you get that straight, because this is an output from the computer that we're measuring. So commanded on time. So from here to here is when the computer is commanding it to be on. Now, while it's on, if we think about how an injector works, it's basically a solenoid at its most basic. So it has a coil, an electromagnet, and it has a little pintle that opens and closes, and it's like a valve. So when it's on, the electromagnet lifts that pintle off the seat to hold it open to allow it to spray. When it's open, all of that voltage flowing in there is collecting inside that coil. And then when it's done, when I release the ground, it has to go somewhere, right? So when it closes, we get that big spike in the pattern. And that's why we see this big tall spike right here. So in this case, it looks like it's a little over 80 volts. Now, there really is no known good that I could tell you for a car because every car is going to be different. Every injector might be a little bit different. As long as they're the same brand and same type, they're probably going to be pretty close. What we want to do is we want to look at multiples of these on the same screen if we can, or test them individually and just kind of remember where the peak was. Because if one is higher, one is lower, that indicates an issue. If I don't get a peak at all, that indicates it really didn't open because my coil didn't hold that energy. It works on the same principle as an ignition coil. Then it comes down, and then we have this other little pintle bump right here. Now, this is going to be the actual point where the pintle closes, snaps shut, and stops spraying fuel. When it does that, that little mechanical stop jolts a little extra juice back out of the coil, so we get that little thing they also call coil oscillation, and then it flattens out. Now over here is the current. So you see they when it opens, or when it's commanded open, should I say, the current rises. It should go up in a nice smooth ramp like this, kind of look like a hill or a ramp. If it goes up sharply or over, there's a problem in the winding. As it goes up, we should see a little dip. This dip is the point where that injector actually opens and starts spraying fuel. So you'll see it's not right at the beginning. It takes a little while because we have to charge that coil up enough to get that thing to move. When it does move, there's a little bit less resistance at that time because it's already in motion. So we get that little dip in the amperage right there to be able to see that. Now, if it's opening at the same time, we're in good shape. If it's opening here, then opening there, then opening there, and being really erratic, that's a problem as well. It could be a bad spring inside. So seeing all these different things and being able to compare them electrically and mechanically on the same screen is very useful for being able to analyze what's going on. So if I do both of these on the same screen, I have them both, I should be able to see the injector open and close. All right, going to be able to do that. And I can verify that it actually is open. How about CAN? We'll talk a little bit more in detail in CAN when we go live on the tool. But what that is, that you need 2 channels in order to be able to test CAN accurately. So high-speed CAN is 2 twisted wires, transmits data at a rate of about 100 to 500 kilobits per second. It's been around for a long time, since about 2016, or 2006, 16 years is what I'm trying to say. Been around since 2006. And actually it's been around longer than that, but it was standardized in 2006. Any network on a vehicle, also, if you want to learn more about that, you can watch the network class. But it uses what we call a voltage differential. So from low to high, what is my difference from top to bottom? And that is my data. Now, one signal circuit is going to be called CAN high. The other one's going to be called CAN low. That's why we need 2 signals or 2 channels to be able to test this. At each end of the data bus, there's also a 120 ohm termination resistor between the high and low circuits. So that's kind of like the end of the line, the stop sign. Here's where the end of the line is. It's usually inside a module. So if we have a problem with the termination resistor, we'll have a problem with the circuit as well. Communication problem in car. So here's just a really quick example of what CAN would look like on a scope. See, I have my CAN high, my CAN low. We see we have a couple different states. Like I said, we're going to talk more in detail about this in a few minutes when we go live on the tool. But these little squares right here are the data packet. And this is my bits and bytes, my ones and zeros going back. Easiest place to test this is also at the OBD2 connector. Needed to know that. Next thing we'll talk about is another popular one. It is cam and crank correlation. So cam and crank correlation allows me to see visually how does my cam sensor line up with my crank sensor. Am I in time? So in this case, we have a crank sensor on the screen. It is an analog pulse generator in this case. It's on a Subaru. And you see I have one gap in there. They call that a single gap. And then we have that same thing twice over here. It's a double gap. So one side has some teeth missing. The other side has double the amount of teeth missing. And that allows the computer to understand where is it in rotation. So is it upside down or is it right side up? One rotation would be from like here to here, right? So it's one time through this pattern. So there's my crank sensor, and this is usually guided component test. Now, guided component test generally is going to be just one sensor at a time. So we need to be able to add channels. So if we can go into our settings, we can go in and add channels. Now, this is on a Zeus, so that has 4 channels, and we see these eyeballs here. We can add up to 3 more. So if we do that, I added 2 more channels on the Subaru because it is a horizontally opposed. It's got 2 cam sensors. So there's my crank, there's my cam, there's my other blip on the cam here, and then there's my cam sensor on the other side giving a blip at the same time. So we can see how they match. Now, if these were offset, I would know that maybe my chain is stretched or I have some other sort of a timing problem in there. If they don't fall inside the right window, I'll know that there's some sort of a problem in there as well. So they need to kind of line up like the cam sensors definitely need to line up like that on this particular car. Now, nice thing about this too is the manufacturer actually publishes a known good cam crank correlation pattern. Not every manufacturer does, but many of them do. So if you just take a look, usually it's in like a cam sensor code type of thing. If you go look inside a cam sensor code diagnostic chart, oftentimes they'll give you those in there. Sometimes it's just published as a cam crank correlation chart. But good to know, judging by timing. Now, what if I don't have a 4-channel tool? I can still do 2 at a time, right? So if I have a 2-channel tool, I can do my crank and my cam, and then I could just unplug that cam and plug it into the other cam and see where they line up, make sure everything's good there. I can do both cams at the same time. Whatever you need to do just to make sure that they relate to each other over time. Back to the 4-channel tool, we have our 2 cam sensors and our crank sensor. And in this case, we added a 4th channel to show us kind of where number 1 was. So we have number 1 there on the fuel injector. So that's being able to use the 4 channels for that. And then also we can separate them out on that tool as well to make it a little easier to see. When it's all jumbled up like this, it's kind of hard to tell what's going on. So we can do that. How about this one? So this is what I'd call who failed first, like who's on first, right? So who failed first? So this was a classic vehicle at this point. It's a 91 Ford F-Series. So it had a 351 and it had a distributor, right? Distributor ignition around the front of the engine. And it would intermittently stall. Could be running for 10 minutes, could be running for 10 seconds. It would just stall kind of seemingly out of nowhere when it wanted to. So we wanted to see, well, what's the problem? Oh, and by the way, I already had the ignition module replaced. But as I said, we always want to test those new parts just in case. So this is a 6-pin connector on there. We can see what the connector view is. Oh, this has got a component test, by the way, so we can see the information that gives us there. And then if we were just testing the coil output, it should look like this. But we're going to test a lot of things on this so we can see. So we have 3 channels on this in this case. We have the crank position sensor signal, which they call PIP. And then we have the ignition output signal. And then we have something that's called spout. So this spout is an input to the ignition module. This crank signal is an input to the ignition module too, and then it goes through the module to the computer. And then this ignition output is an output from the module. So the crank sensor goes through the module out to the computer, control module, and then the computer then sends this spout back to the ignition control module. And this helps with timing advance. And then based on these signals, it makes a calculation and decides when the ignition needs to fire. So there's my ignition signal. So we recorded it with all these 3. Didn't have to use 3, could have just used 2, but in this case, I wanted to see the full kind of the loop there. So we said, all right, we'll record it, and then it stalled. So like, great, cool. So I captured it. We'll see what happens. So we zoomed out, and we can see, I think it's pretty obvious who failed first. Right, this guy in the middle right there, the actual ignition signal. So the crank sensor was working right along. The spout signal was working right along, and that ignition signal failed. So in this case, that's a bad ignition module in that case. Now, I know they had problems with the ignition module, but this just kind of goes to show you just because it's new doesn't mean it works. And now we can see it was about half a second. It was 594.68 milliseconds from when that ignition signal stopped to when the vehicle actually shut off and stalled. And as you can also see that they're getting further and further apart, the frequency is increasing because the engine is rotating slower. So the crank sensor is going to send its signal slower. Now, without having the scope, like I said, half a second. Who failed first? Within half a second of each other. We can see that plain as day using this method. But if I was just to rely on scanner data, I might never have found this, right? Now, we could have used 2 channels. Could have used the crank sensor versus the ignition, or the ignition versus the spout. If we had done the crank versus the spout, we wouldn't have seen anything. We just kind of have to move it around, right, till we find what we're looking for. But yeah, it's pretty obvious being able to look at the multiple different channels in order to be able to do that. All right, now let's get even a little bit more advanced. This is going to be the last example before we go live here. How about a brushless fuel pump? Brushless fuel pump works totally different than a regular brushed fuel. I should say regular, but different than a brushed fuel pump. So what it does is it has 3 sets of coils on there where it can reverse the polarity depending on where the permanent magnets are on the stator here. So we have the magnets on the rotating part, and we have the coils on the non-rotating part, versus on a brush motor, it's the other way around. So if we look at this animation here, these coil windings can be reversed. So right now this one's black, which means it's off. I have this south magnet, so it turns to south to repel it and push it along. And then when that's done, it turns off, waits for the north to get by, then it turns to a north polarity, pushes it along, right? So it's used to repel those permanent magnets around. So I can actually spool up pretty fast. This is a way slowed down animation of it, but you can kind of see how it's able to reverse polarity. And we can actually see that with a scope, how it reverses the voltage as well. So here's just an example. Fuel pump control computer has what we call a V, a U, and a W circuit, and then ground. So these 3 circuits are my 3 coils, and we can see whether or not they're in a positive or negative state by looking at it on a scope. All right, so here's my U, my V, my W. They're 120 degrees offset from each other, which gives me a 360-degree turn in there. So I actually be able to measure how fast it's turning. I can see whether the polarity is up or down by also adding this other channel over here for my current. I could do 1 voltage with the current at the same time and kind of see what's going on there. We can see that as well, just to understand how the voltage and how the current flows through that. But this is a definite multi-channel necessity if you want to test how one of these works, just because it has so many different control signals. If you want to learn more about this, then go check out the fuel pump video that we have on our YouTube channel as well. All right, so let's go live on the tool. I see I got a couple questions on Zoom. I got a couple questions. Actually, I got a lot of comments on YouTube today, so that might take a little bit. I also want to say before I move over, say hi to Frank down in Newport News. He's got a class going on down there, Mr. Frank Loving. Good DSD of ours down there in Virginia. Glad you could tune in tonight, and hope you guys are getting a lot out of this class. All right, so here we are on our Triton, and as I said before, Triton, Zeus, Veris, Modus, Vantage, any of those tools, any of our tools with the scope built in is going to have this guided component test database in there. So there's a few things I want to talk about on that. So first and foremost, built into the tool, before I even ID a car, you'll notice the very first thing that's highlighted on the screen there says classes. Now that just got moved to the top of the list with the latest software update. So 21.4, that is up at the top of the list. So this is where this is really helpful. So when I usually show this on the Zeus, we're like, okay, I can see it on the screen regardless. But on a tool like this where I have to scroll, well, if I have it at the top, it's going to be more top of mind, right? So there are many built-in classes inside this tool. So if we go in there and we go into power user tests, there are dual channel tests in there. If we look at the second test right there, and we can see multiple different generalized tests in here. So this is not a vehicle specific test, right? So it's going to have our generalized tests, so like CAN bus, cam and crank relationship, EGR solenoid, flex ray bus, injector and oxygen sensor, throttle position sensors 1 and 2, because we have 2 throttle sensors, right? Wheel speed sensors, able to do multiple channels, compare different wheel speed sensors with each other. You can do that as well. So these are really generalized for really to work with anything. Kind of gives you a general ballpark, and then you might have to change a little bit here and there. But as I said, it's not vehicle specific. But if you want vehicle specific, we can do that as well. So let me back up here, and we'll go into a vehicle. So I have my BMW demo board here. So I'll go into BMW, and it's a 2012 328i with N52 KP. All right, and then once I load the vehicle, remember how I said there's over 5 million tests in here. There's 12 different possible systems that could show up on a car. In this case, we got 4. So I'm going to go in the engine because I know there's a couple different things I can check in. Now, first thing is, what if I wanted to do a cam crank correlation test on this vehicle? Well, I can go into my crank sensor, and I can go into, let's say, signature. So it's going to give me a wealth of information before I even start. So it's going to, first off, it's going to tell me where do I hook up. So there's color-coded things on the top, color-coded connectors, color-coded connectors on the top, which corresponds to your color-coded scope leads. So yellow goes to crank signal, black goes to no good ground. And we should use the lab scope to check the waveform. And if we look down a little bit further, it gives me my connector view, right? So we have our connector on the crank sensor. And then I also have my computer connector down here as well. So if I have an alternate connector point, it'll give me that. So there's my ECM points. And if I go all the way down to the bottom, if it's a signature test, it's going to have my known good pattern on the screen as well. So all I have to do is hit view meter. I got to use my finger for that. It's a touch screen, right? Hit view meter. It is going to automatically set the voltage, as I say, automatically sets the time base, as I said. And then as you can see, I can scroll up this background and see if they match. Now it's going by kind of fast, but they do match, other than they're upside down. And that's the signal generator's fault, right? For putting it out flipped upside down. But we can see that they do match. So I can understand, okay, this is there, that is good. Right, so I can see that. Now, what if I wanted to add in my cam sensor as well? So there's 2 cam sensors on this vehicle, so I could do one at a time. So in order to do that on this Triton, and it would be hold true for the Modus and the Vantage as well, is up here on the right-hand side, on the top right-hand corner, there is this 4 arrow. If I click on that, makes it full screen, and then it brings up my settings down here. So if I want to turn on my additional channel, we look over here on the left-hand side, we've got this blank. Click on that, opens up our eyeball, and then we can have our second channel there. Now, when you add additional channels on the guided component tester, it is preset to whatever it is when they saved it. So it's not necessarily going to be where you want it. So you might need to make a change. So make sure the probe is correct. So in this case, it's voltage, and then change the scale. So in this case, I'm looking at 20 volts. That's a 5-volt signal. So I want to get it down to maybe like 10 volts and make it a little bit. So when I do that, we can see the signal changes a little bit. I can use these numbers on the right-hand side to move them up and down so I can see them a little bit better in relation to each other. Put the number 1 at the bottom, put the number 2 at the top if I want to do that as well. All right, so we can move them around and we can change how they are. Now, we would want to see how do they relationship to that? How do they relate to each other? In this case, we're not going to see really anything lining up because it's a simulator. It's not actually meant to send the signal out correct. But on a normal car, you would see where the cam sensor rises and falls, crank sensor. Be able to see that. So that's adding the channels. Very easy. As I said, it's that 4 arrows on the top right. Blows it up, makes it real easy to do. Now, what if I have another 2-channel test I want to do? I'm going to back up here a little bit, and then you'll see right above my crank sensor, I got CAN bus. So I'll go into CAN bus, and you see we got information on CAN bus, and then I also have my signature. So we'll go in there. Now, I also need to plug it into my CAN bus. I got to remember to do that. Otherwise, it's going to be not a CAN bus. Okay. So in this case, this is going to be automatically setting up for a 2-channel test. So a CAN bus high and CAN bus low, and then lab scope should be used. So if I scroll down a little bit, it gives us the location to test it. And then it gives us, I'm trying to scroll up without my finger. There we go. It gives us the known good voltage, and it gives us our known good path. If I hit view meter, it's going to go in there. It's going to set it up for me, and there's my CAN bus. If I come down here a little bit more, we can see there's my known good. Here's my pattern right here. I'm going to actually bring them a little bit closer together because that's just me. And there we go. I can see what's going on with the CAN bus and see if it's the same. Now, that is a known good CAN bus pattern. What if I wanted to see it a little bit closer? What if I wanted to get in a little closer? We can actually change the time base down here on the bottom. So if I click on the time base, that's 500 microseconds. Let's go up to a millisecond, make it twice as long. So what that's going to do is that's going to zoom out for me a little bit, and it makes it smaller. So what if I wanted to make it bigger? We can go down the other way, go to 200 microseconds, and then that gives me my time. Now you see it's moving around a little bit, being a little jumpy. I can also move around this trigger point right here, this plus sign, and move it to kind of where it crosses the pattern, and that allows me to move it around. Once I'm done with that, I probably want to make some measurements in here, see what's going on with this. What are my voltages? So if I stop my recording, I'm going to freeze it on the screen, and then I can turn on my cursors, which is right next to it. and be able to measure. So I said I was going to talk a little bit more in detail about it. So let me take number 1, put it over there. Number 2 is probably good, right? So you can see we have 2 states. We have a flat line over here, and then we have, remember how I talked about these being our 1s and 0s, our data. When it's level and not doing anything on a real live car, you're going to see about 2.5 volts. That'd be called an idle signal. It's just sitting there not transmitting. When it transmits, the high side goes from 2.5 up to 3, about 3.5, 3 3/4. Bottom side is going to go from that 2.5 down to about 1 1/4, 1.5. So as we can see here, the difference 0.928 and 1.009, that's almost a 2-volt differential. Remember how we said we need about a 2-volt differential in. So that is good. We want to see flat tops. We want to see flat bottoms. They should be pretty much the same on both sides, and we're really darn close. Especially considering this is a simulator, about as close as we're going to get on this pattern. Now, also one last thing, on some vehicles, you will see this large bit at the end. They call that an ACK bit or an acknowledgement bit. That is basically the period at the end of the sentence, what I like to say. So the computer will send its data, and then when it's done, it says, okay, that's me, I'm done. Whatever's next is not me, right? So then another module will transmit their data and so on. So as we can see, we can analyze that pretty easily. And that is, once again, that is a 2-channel test. You have to really use a 2-channel test to do this. Otherwise, you're not going to be able to see whether or not one's higher or lower, or whether or not we have just half the packets dropping out or something, which are all possible issues. Now, as I said, these are kind of high level. We do have other classes on networks as well that you could take if you wanted to check that out. So,
and with that, that is our time here today. So make sure you tune in for new diagnostic content every week. We will be premiering a new video every Wednesday at 7 p.m. UK time. So make sure you check it out on the YouTube channel. If you're watching, well, of course, you would be watching this on YouTube, but make sure you subscribe, thumbs up, ring the little notification bell so you know anytime we post new content. And it's youtube.com/SnapOnDiagnosticsUK. With that, time for questions. If you have any questions, just feel free. Once again, if you're watching this on a premiere, just leave it in the live chat and we'll answer those. Otherwise, leave a comment under the video and we will get to those as we monitor those comments as well. So I'd like to thank you for taking a little bit of time out of your day to learning a little bit more about how you might be able to be more efficient at diagnosing vehicles using some of the information that we've given you today. Hopefully we'll see you next week. Hopefully you can watch and see you on any of our other videos. Have a good week, have a good night, and take care.